Alright, let's start talking about the trig formulas. So we'll start with the sum and difference formulas, and those are sometimes also called the sum and difference angle formulas. So there's a worksheet here with all the formulas on it that we're going to talk about. So in this video we're going to establish these four identities here, or four formulas here, and then in the next video we'll talk about these two here. Okay, so what's nice about these trig formulas is you can establish the cosine of alpha plus beta and the sine of alpha plus beta just from a picture, and then just using some algebraic manipulations you can pretty much get everything else on this paper. So that's pretty nice. So anyway, if you want to copy this to follow along with, check the video description. There's a link in there. Click that link, open this up, print it out, and follow along if you'd like. Okay. So we're going to establish these four here. Well, two of them with the picture, and then the other two come from algebraic manipulations. And the picture is going to look pretty goofy, and it might just look like we're just kind of making stuff up for no reason. But near the end of the video, we'll talk about kind of where that picture comes from, what's the motivation behind it, and how it actually works in more generality than what it looks like. Okay, so the picture is going to look like it only works for acute angles, alpha and beta, but it's actually going to work in more generality. Okay, so we want to establish cosine of alpha plus beta equals this mess, and sine of alpha plus beta equals that mess. So we're going to draw a picture that involves angles alpha and beta. Okay, so that's what we're going to do. And we're going to use some properties from geometry and things like that too. Okay, so let's go ahead and get started. So we're going to draw a big rectangle. Okay, so here's a rectangle, and then we're going to put a diagonal in here. Close enough. Okay, and then also little line segment out to here. And now what we want to do is from this corner of the rectangle, what we want to do is drop a perpendicular down to here. So that's going to be perpendicular. Okay. And now we also want to drop a perpendicular, actually first we'll extend this so that this is perpendicular, and then we'll drop another perpendicular line segment from here down to here. Okay, and then one more from here to here. Okay, so it's an incredibly goofy picture, but we'll see, again near the end of the video, we'll see where it comes from, why it is the way it is. So one more thing that seems kind of goofy is this length of the diagonal here that we drew near the beginning. We're going to make that length 1. Okay, why is it okay to make that length 1? Again, we'll see near the end, but short answer is you can kind of put this inside of a unit circle, and when you put this picture inside of a unit circle, this is actually going to be the radius. So this would be the center of the unit circle. This will be the point on the unit circle where this angle hits it. Okay, so center of the unit circle, a point on the unit circle, this distance is the radius, so radius is 1. Okay. Now, does it have to be 1 for this to work? No, not at all. This can really be anything else, any other number. But if it's 1, that keeps things pretty simple, and we don't lose any generality. Okay, things will still work in more generality, even if this is not 1. Okay, so what we're going to do is label this angle alpha right here, and this right here is angle beta. Okay, let's zoom in a little bit on that. So here's angle alpha, here's angle beta, and now they're acute angles, right, because they're sitting inside of right triangles here. Okay, so alpha's inside of this right triangle here, and beta's inside of this right triangle here. So this is a right angle, so this is also a right angle over here. So this is a right triangle. So it looks like this is only going to work for acute angles, but actually the same principles can be applied for more general angles. But anyway, we'll talk about that again later. So if this is alpha, this is beta, this whole thing is alpha plus beta. Okay, so what's significant about that? Well, first, we're going to use a property from geometry that says if you have two parallel lines or line segments and they're cut by a transverse axis or a transversal line, then the alternate angles here, those are congruent. Okay, so in other words, they have the same measure, the same size, they're equal to each other. Okay, they have the same measure and size. So two parallel lines or line segments cut by this transversal line here, this angle equals that angle, and also this angle equals this angle. Okay, but the point is these alternate angles here, they're congruent, they're the same. So how does that apply here? Well, if we look back at our rectangle that we drew, the top and the bottom, they're parallel to each other, right? Just because it's a rectangle, so that's just, what a rectangle is. These two sides are parallel to each other, and they're cut by this diagonal here. So this angle equals this angle up here. Well, we know that this is alpha plus beta, the way we labeled it. So since this is alpha plus beta, then this angle up here has to be the same. So it's also alpha plus beta, okay? Okay, so again, parallel lines or line segments cut by the transversal right here. So this angle has to be equal to that angle up here. Since we already know this is alpha plus beta, then this also has to be alpha plus beta, okay? Now, so this gives us this angle over here. Now we also need this angle in here. So how are we gonna get that angle? Well, we're gonna start using the same property we just used. Okay, so this whole line segment right here is parallel to this little tiny line segment right here. Okay, so if we imagine extending this big line right here, parallel to this line right here, and, whoops, and they're cut by this transversal right here. Okay, they're cut by this right here. So actually this angle and this angle are equal. Okay, but we already know that this angle is alpha, so what that means is that this angle up here also has to be alpha. Okay, this angle also has to be alpha. Okay. So again, imagine extending this little tiny line segment here, then we have a parallel, we have two lines that are parallel right here. Okay, so line right here, they're parallel, so they're cut by this transversal right here. So just from that property in geometry, this right here is congruent to this angle right here. Since this is alpha, this also has to be alpha. Okay, now we're going to use that, we'll zoom in on that. We're going to use that to get this angle here. Well, if this is alpha, this actually also has to be alpha, okay? This also must be alpha. Why is that true? Well, because since this is 90 degrees, then this entire thing right here is also 90 degrees. Okay, let's make that a little better. Okay, so 90 degrees. So this whole thing is also 90 degrees right here. So if this piece right here is alpha, then this has to be what's left over, which is 90 degrees minus alpha. Okay, so if you have the whole thing is 90 degrees. Okay, this whole thing is 90 degrees. We know this part is alpha. Then what's left is 90 degrees minus the alpha. Okay. Okay. So alpha plus 90 degrees minus alpha equals 90 degrees. So that's one way to check it. So since this is 90 degrees minus alpha, then that automatically means that this must also be alpha right here. Okay, so that's why we can just automatically say, since this is alpha, this also has to be alpha. So since this is 90 degrees minus alpha, and this is a 90-degree angle right here, then this third angle left over must also be alpha. Okay, because just like here, these two angles have to add up to 90 degrees because of this 90-degree angle right here. The exact same thing is true for these two angles because of this 90-degree angle. Okay, so this angle and this angle must add up to 90 degrees. Since we know this is 90 degrees minus alpha, this has to be alpha because these two angles add up to 90 degrees. Okay, so that tells us that this is alpha, and that's what we needed to know. So let's zoom back out a little bit, and we'll just recap that real quick. So extend this little line segment here, then it'll be parallel to this line segment right here. They're cut by this transversal line right here. So that means this angle and this angle, they're congruent. Since this is alpha, this must also be alpha right here. Okay. So since this is alpha and this is a 90-degree angle, then this has to be 90 degrees minus alpha because this and this have to add up to 90 degrees because of this 90-degree angle. Okay. Well, now this angle, which we just found out, and this angle must also add up to 90 degrees because of this 90-degree angle. Okay. So since this is 90 degrees minus alpha, the only thing this could possibly be is alpha. Okay. All right. So that's great. That's wonderful. Zoom back out. Okay. Now let's start labeling some sides here now that we have all the angles that we need. So we'll erase the angles we don't really need labeled anymore. So first of all, let's get rid of this too. We don't really need anything labeled over here. Okay, all we had to know is what's this angle and what's this angle up here. All right. So now that we have this angle, remember this, since this was a rectangle in the beginning, then this is a right triangle. Well, first of all, this is a right angle, which means this right here is a right triangle with hypotenuse 1. Okay? So the fact that this has hypotenuse 1 simplifies things quite a bit, because what we want to do is label this side and this side in terms of trig functions. Okay? because that's as good as we can do because we don't really know the size of alpha and beta. Okay, from the picture we know that they're acute, but we don't know their exact measurements, so we can't get any more specific than just with trig functions. Okay, so forget about all this other stuff over here and just look at the right triangle here. So here's one leg of the triangle, another leg of the triangle, and the hypotenuse of the triangle. So what we want to do is label this triangle based on trig functions of this angle here. So remember, trig functions in a right triangle, cosine of alpha plus beta is adjacent divided by hypotenuse. Okay? It's adjacent divided by hypotenuse. Well, the hypotenuse is 1. Okay, the hypotenuse is 1. So instead of hypotenuse, we'll just have 1. But when you divide something by 1, you're really pretty much doing nothing. Okay, so that doesn't change anything. So adjacent divided by 1 is just adjacent. So actually what that tells us is that the adjacent side is exactly equal to the cosine of alpha plus beta. Okay, so that's helpful. So here's our angle alpha plus beta. So the adjacent side exactly equals cosine of alpha plus beta. Okay, that's what we just found out. Okay, again, cosine of alpha plus beta is adjacent divided by hypotenuse, but hypotenuse is just 1, so the cosine of alpha plus beta equals the adjacent side. Okay? For the exact same reason, the opposite side is the sine of alpha plus beta. Okay? So sine of alpha plus beta is opposite over hypotenuse. Okay, here's alpha plus beta, so the sine of alpha plus beta is opposite side divided by the hypotenuse, but the hypotenuse is just 1. Okay? So if you divide by 1, you're not really doing anything. So the sine of alpha plus beta is just the opposite side. So this is sine of alpha plus beta. Okay, this whole side right here. Okay. All right, now how's that help us? Well, what we're going to do now is determine the length of this piece right here, this whole piece right here, and then this little piece right here, and then we're going to use that to get the formula for cosine of alpha plus beta. And we're also going to get the length of this piece right here and this piece right here, and then use these two to get the formula for sine of alpha plus beta. Okay, so that's kind of where we're heading with this goofy picture. And again, we'll see why this picture actually isn't as goofy as it looks near the end. But moving on. So, all right, now let's focus on this right triangle with just beta in it. Okay, so we'll rotate that. And poorly drawn, I can see now, but we'll just pretend that's a right angle. Okay, so since this is a right angle, this is also a right angle. Now let's just focus on this right triangle in here. So forget that angle alpha for now. Just focus on this right triangle here. So we have hypotenuse equal to 1. We have this leg right here, right angle right here, and then this leg right here. Okay, so we'll just focus on that right triangle. Now this here is angle beta. Okay, so if that's angle beta, then cosine of beta is adjacent divided by hypotenuse. But the hypotenuse is 1, so just like with what happened up here, you know, cosine of alpha plus beta is adjacent divided by hypotenuse, but the hypotenuse is 1, so the adjacent side is the cosine. Well, the exact same thing is going to happen in here. So it's a completely different triangle, but it has the exact same hypotenuse. The hypotenuse is 1. Okay, so cosine of beta is adjacent divided by hypotenuse. Okay, cosine of beta is adjacent divided by hypotenuse, but again, the hypotenuse is 1, so you're not really doing anything. Okay, so we just have nothing going on there. So cosine of beta is the adjacent side. So here's beta. The adjacent side is this side right here. So this whole thing is cosine. Cosine of beta. We'll cut in there a little bit. Okay, so that's cosine of beta. And likewise, let's get rid of this. Yikes. Okay. Likewise, what's happening? This is going to be the sine of beta. Okay, this right here is the sine of beta. Okay. Okay, again, because we have this right triangle here, so here's our angle beta, here's our right angle, here's one side of the right triangle, another side of the right triangle, here's the hypotenuse. Since the hypotenuse is 1, this equals the cosine of beta, this side is the cosine of beta, and this opposite side is the sine of beta. Okay? All right, now let's focus on this little triangle right here. So we'll zoom in a little more. Okay, now we're pretty much going to do the same thing that we did before, but now things get a little more complicated because our hypotenuse is no longer 1. Okay, when we looked at these two triangles here, we had the hypotenuse equal to 1. but now it's going to be a little more complicated because the hypotenuse is actually the sine of beta. Okay? But we're going to see it's actually not that much worse. Okay, okay, so let's, we don't actually need this here, so we can get rid of that extension there. All right, so we have that going on there. Now, cosine of alpha is adjacent divided by hypotenuse. So let's go ahead and write that down using a different color. Cosine of alpha is adjacent divided by hypotenuse. Okay. So here's the adjacent side, here's the hypotenuse. The hypotenuse we see is the sine of beta. Okay. So the cosine of alpha equals adjacent divided by the sine of beta. Okay. So if we multiply both sides by the sine of beta, then what we have is cosine of alpha sine of beta equals the adjacent side. Okay, and that's actually what we're after. We're trying to figure out what's this side here, what's this side here. Okay, so cosine of alpha, since it's a right triangle, it's adjacent divided by hypotenuse. We know the hypotenuse is sine of beta. We found that out earlier. And if we multiply both sides by sine of beta, then what we have is cosine of alpha sine of beta equals the adjacent side. So this adjacent side equals cosine of alpha times sine of beta. That's what we just found out. So this right here is cosine of alpha. So this is cosine alpha sine beta. Okay. Let's maybe make that a little more legible. Just a little bit. Okay, so that's cosine of alpha sine of beta. Marginally better. Okay, so and we'll do the same thing with this side now. Fix this also. All right. So cosine of alpha is adjacent over hypotenuse, so we use that to figure out the adjacent side right here. So now we have to figure out the opposite side right here. So let's go ahead and do that. Okay. So sine of alpha equals the opposite side over the hypotenuse. And again, the hypotenuse is the sine of beta. So sine of alpha equals the opposite side over the sine of beta. Okay. So here in this right triangle right here, sine of alpha is the opposite side right here divided by the hypotenuse right here. We know the hypotenuse is sine of beta. So we have that. So now if we multiply both sides by the sine of beta, then what we have is sine of alpha sine of beta equals the opposite side. Okay. So this opposite side right here is exactly equal to the sine of alpha times the sine of beta. Okay. So let's zoom out a little bit. Wrong color. So this right here equals sine of alpha sine of beta. Okay. So that's sine of alpha sine of beta equals the length of this opposite side right here, the side opposite angle alpha. All right, now, since, we'll zoom back out a little more. Since this is sine of alpha sine of beta, and what we have right here is a rectangle, okay, notice right angle over here means right angle over here. And since this is a right angle, this is also a right angle. So this last angle left over also has to be a right angle. So the point is this makes a rectangle right here. And since this is sine alpha sine beta, then this opposite side over here must also be sine alpha sine beta. So this is sine alpha sine beta. Okay. Okay, so that's what's happening there. All right. Now the next thing we want to do is figure out, all right, what's the length of this side right here? So, and also this side right here. Okay. So let's go ahead and do that. So if we look at this triangle, so pretty much we're just going to do the exact same thing we just did, except now we're going to look at this triangle right here. So look at this triangle right here. Okay, so we have our right angle right here, and then here's our angle alpha, so that's our angle of interest now, and the hypotenuse is cosine of beta. So this is actually going to be exactly what we've been doing, but remember for the first two triangles we looked at, they had hypotenuse 1, it was relatively simple and straightforward. But this third triangle, the one that we just looked at, had hypotenuse sine of beta, so it was a little tiny bit more complicated, but not too bad. Okay, now we're going to do the exact same thing again, but now the hypotenuse is cosine of beta. Okay? But really the exact same stuff is going to apply. Okay? So again, here's our angle alpha. So actually, remember it's alpha and alpha, so up here it's the exact same angle. So now we're going to do exactly what we just did, but we have a different hypotenuse, okay, and we're inside of a different triangle. But it's still a right triangle, so again, we're looking at this right triangle right here, okay? And we're going to do the exact same thing we just did. So, cosine of alpha equals adjacent divided by hypotenuse, okay? We know the hypotenuse is the cosine of beta. We found that out earlier. Okay, so this hypotenuse right here, that whole thing is cosine of beta. Okay, we already know that. So cosine of alpha equals adjacent divided by cosine of beta. Okay, so now we can multiply both sides by the cosine of beta. So we have cosine alpha, cosine beta, and then that's going to give us the adjacent side. Okay, so the adjacent side of this right triangle here, the adjacent side to angle alpha, exactly equals cosine alpha, cosine beta. Okay, so let's go ahead and label that. You'll label that in red. So all these colors are running together now. So this whole thing here is cosine alpha, cosine beta. Okay. Because remember, the right triangle that we're looking at goes from here to here, and then up to here, and then down here is the hypotenuse. Okay. So this entire adjacent side is the cosine of alpha times the cosine of beta, is what we just found out right here. Okay. All right, and then one more thing to do. Oops. Okay. Now we'll do the exact same thing, but now we do the sine to get the opposite side. So the sine of alpha equals opposite divided by hypotenuse. Okay, but the hypotenuse is the cosine of beta, so the sine of alpha equals opposite divided by the cosine of beta. Okay, so multiply both sides by the cosine of beta, so then we have sine of alpha cosine of beta equals the opposite side. Okay, so what's the opposite side? So here's angle alpha, the opposite side is going to be this angle, or sorry, this side right here. Okay, be careful, it's not this side, okay, it's not this side right here, not this, because we're using, this is our hypotenuse from here all the way up to here. Okay, since this is the hypotenuse, then this side over here is the opposite side, not this right here. Okay, so be careful about that. Yeah, we actually don't really, you know, we kind of do need it because it sets off what this is, but just be careful about that. We're looking at this right triangle in here, okay? So let me put that back in because, you know, we kind of do need it. All right, but anyway, so the opposite side is sine of alpha times the cosine of beta, so let's go ahead and label that, I guess in red to keep it consistent. So this is sine of alpha cosine of beta. All right, now we're actually ready to go to establish these identities. So let's zoom back out and look at this whole picture here. Okay, I'm just hoping we can zoom out farther, but I guess not. All right, so here, up here, what do we have? Here's cosine of alpha plus beta. Okay, that's from here to here. Now remember, since this is a rectangle, then this is also the length of this side right here. Okay, so from here to here, what we have is cosine of alpha plus beta. Well, notice, let's zoom in on this now as we just focus on that. Okay, so if this is cosine of alpha plus beta, this is sine of alpha sine of beta. If we add these two together, okay, so add this to this, and you get the whole thing, right? So add this line segment to that line segment, you get the entire thing. Well, we know what each of these things, we know what they all are. Okay, so this is cosine of alpha plus beta. If you add it to this, you're going to get that whole thing. Okay, so in other words, cosine of alpha plus beta plus sine of alpha sine of beta equals cosine alpha cosine beta. Okay, so let's go ahead and write that down off to the side. Completely out of room pretty much, but anyway, let's come up here. So cosine of alpha plus beta plus sine alpha sine beta equals cosine alpha cosine beta. So cosine alpha plus beta, okay, plus sine alpha sine beta equals cosine alpha cosine beta. Okay. Now, of course, that's not how the formula is stated. So if we subtract sine alpha sine beta from both sides, then what we end up with, we can erase this now, we don't really need it. What we end up with is cosine of alpha plus beta equals cosine alpha cosine beta minus sine of alpha sine of beta. Okay. So cosine of alpha plus beta equals cosine alpha cosine beta minus sine of alpha sine of beta. And we see that actually is the first identity on this list here. cosine alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. Okay, so this is one of many ways really to establish that. Okay, and now we'll do the exact same thing to get the other one for sine. Okay, but that one's actually going to be a little bit easier because we don't have to do this kind of thing here where we subtracted from both sides. Okay. Okay, so this whole thing, this whole thing is sine of alpha plus beta. So since, again, this was a rectangle, remember at the very beginning, it's a rectangle, so this whole side right here is also sine of alpha plus beta. It's completely ruining this picture now, it doesn't really matter. So since the whole thing is sine of alpha plus beta, and we also know that since this piece right here is sine of alpha cosine beta, then because this right here is also a rectangle, this piece right here is also sine of alpha cosine of beta. Okay? So if you take this piece right here, add it to this piece, you get the entire thing. So if we zoom in a little bit, we see if we take sine of alpha cosine of beta, this piece, and then add it to cosine of alpha sine of beta, this added to this piece right here, then that gives us the entire thing, but the entire thing is sine of alpha plus beta. Okay, so if we zoom out, let's go ahead and write that off to, we're really totally out of room here, we'll just write it over here. So what we just see then is that sine of alpha plus beta, so in other words, the length of this entire side equals the length of this piece plus the length of this piece. So sine of alpha plus beta equals sine alpha cosine beta plus cosine alpha sine beta. It's cosine alpha sine beta. Okay, so that's the other formula there. Okay, so when we look at our formula sheet here, we see sine of alpha plus beta equals sine alpha cosine beta plus cosine alpha sine beta. Sine alpha cosine beta plus cosine alpha sine beta. Okay, so that's what's going on there. All right, now a couple more things to point out. We also want the ones for alpha minus beta. That's pretty easy to get using algebraic manipulations, and we'll talk about that soon. And also what we want to do is show why this will work in a little more generality. So, and also why it was okay to let this be 1. So let's erase this whole picture here, and then we'll show kind of where that picture came from, and then we'll talk about establishing these for the alpha minus beta. Okay, so if we draw a unit circle here, so does it have to be a unit circle? No, but again, it just makes things a little simpler. So what we're going to do right here is talk about where that picture came from. So if we do this, let's zoom in on this. Here's our angle alpha, put this right here, here's our angle beta. Okay, right here, if we drop this perpendicular, we're gonna have that there, drop a perpendicular here, drop a perpendicular here, and then extend this perpendicular right here. So does that look familiar at all? Yeah, it's a significantly scaled down version of what we just had, okay? So here is the length 1, because this is the center of the unit circle, here's a point on the unit circle, so this is the radius, so the length is 1. Okay, and then if we draw this over here and this over here, that completes our rectangle that we had. Okay, so here's our rectangle that we started with. Okay, and then we put this diagonal in there, which is the radius of the unit circle. Okay, so that's kind of where this came from, is just you can set it up inside of the unit circle and then label everything in terms of alpha and beta like we did, but it's just a little easier and a little less clutter to do it outside of the unit circle. But anyway, that's where all that stuff comes from. It just comes from setting it up inside the unit circle. And a lot of what we did can be generalized and extended to quadrant 2, 3, and 4. So it's not just true for acute angles alpha and beta. Okay, alpha and beta can be really in any quadrant, it'll work. And there are other ways to establish these identities as well. So anyway, that's just a little behind the scenes of what happened there. So you can think of it as being set up inside of the unit circle. So that's where that diagonal of length 1 came from the radius of the unit circle. And again, if you want to use a different circle with a different radius, it will totally work, but it'll just be a little more complicated. Okay, so anyway, let's get the other two formulas. So cosine alpha minus beta, sine of alpha minus beta, and that'll be it for this video. So cosine of alpha plus beta equals cosine alpha cosine beta minus sine of alpha sine of beta. Okay, so what we're going to do here is use even odd properties. So what we want to establish is the cosine of alpha minus beta. Okay? Cosine of alpha minus beta. Well, alpha minus beta, okay, alpha minus beta, that's actually the same thing as cosine of alpha plus negative beta. Okay? So if you say alpha minus beta, okay, that's the same thing as just saying alpha plus negative beta. Okay? So we already know what the formula for the sum of two angles is. So if we have alpha plus beta, the formula is blah, 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 you know, this thing right here. So what if we have alpha plus negative beta? Well, then the formula is going to be cosine of alpha, cosine of negative beta. Okay, so now instead of alpha plus beta, we're doing alpha plus negative beta. And then minus sine of alpha times the sine of negative beta. Okay. Okay, well now remember our even odd properties from way, way long ago. Cosine of negative some angle just equals cosine of that angle. Because remember, cosine is an even function. Likewise, sine is an odd function. Okay, so I'm writing this in terms of theta, but it does not matter what goes inside the cosine of the sine, whether it's alpha, beta, theta, 2, pi, any number, whatever. Cosine of negative a thing is just cosine of that thing. Sine of negative a thing is negative sine of that thing. Okay, so what's going to happen then is this simplifies to cosine of alpha, cosine of beta. Okay, so that's nice. Cosine of negative beta equals cosine of beta. And then this becomes minus sine of alpha times negative sine of beta. Okay, because sine of negative beta is negative sine of beta. Okay. So because sine is an odd function, so we talked about that a long time ago. So what we have is negative times a negative, so this actually becomes a plus. So plus, and then no more negative here. Here's what we have is negative, or minus sine alpha times negative sine beta, so two negatives multiplied together make a positive. So then actually what happens is cosine of alpha minus beta equals cosine alpha cosine beta plus sine alpha sine beta. Okay, terrible handwriting. So cosine alpha minus beta equals cosine alpha cosine beta plus sine alpha sine beta. And if we look at our formula sheet, we see that's what we have here, cosine alpha cosine beta plus sine alpha sine beta. Now one more to do, and it's going to be pretty much exactly like what just happened. We're just going to do the same kind of thing here where we have sine of alpha minus beta and then write it as alpha plus negative beta. Okay. Okay, so sine of alpha plus beta equals sine alpha cosine beta plus cosine alpha sine of beta. So now what we want to do is establish sine of alpha minus beta. Okay, but remember, sine of alpha minus beta, that's the same thing as sine of alpha plus negative beta. Okay. So we know what the formula is for that. So sine of alpha plus beta is sine alpha cosine beta plus cosine alpha sine of beta. So if we replace beta with a negative beta, then what we have is, so alpha plus negative beta, that's going to be sine of alpha cosine of negative beta plus cosine of alpha sine of negative beta. Okay, and then again we'll just use even and odd properties to simplify. So remember, cosine of negative beta is just the same thing as cosine of beta. So that's sine of alpha cosine of beta, and then plus cosine of alpha. So this, because sine is an odd function, this simplifies to negative sine of beta. Okay, so that's what's happening there. All right, and then plus cosine alpha times a negative sine beta, so positive times a negative, so this becomes a minus sign in here, and then that minus sign goes away. So then what we end up having is sine of alpha cosine of beta minus cosine of alpha sine of beta. Okay, and that's the fourth sum difference formula here. So sine of alpha minus beta is sine of alpha cosine of beta minus cosine alpha sine beta, and we see that's what we have on the sheet here. Sine of alpha minus beta is sine of alpha cosine of beta minus cosine alpha sine beta. Okay, so that establishes those first four formulas here on the sheet, and then in the next video we'll talk about the tangent ones, and then we'll do some examples, and then move on to the other formulas here, okay? So that's an explanation for sum and difference formulas for sines and cosines.